The rock in the figure below is traveling in a vertical circle. Determine the minimum speed the rock could have without the string becoming slack. A mass for the rock and the radius of the circle are given. So first, let's just kind of analyze what would be happening in a dynamic situation like this. First of all, the rock is always going to feel its weight. It's going to be pulled toward Earth, no matter where it's located in the circle. And that's actually critical to the problem. In addition to this force, there'll be a tension force created by the rope. But that tension force can change quite a bit in magnitude. Now, since this is a vertical circle, and the rope always pulls in towards center, the rope pulls in such a way that it cannot speed up the particle nor slow it down. The only thing here that could speed it up or slow it down would be gravity. And as we've seen in the past, when an object moves up in a gravitational field away from Earth's center, then it would lose kinetic energy. And it would gain gravitational potential energy. So that means that at the peak, our object is moving the slowest that it will move. And at the bottom, it will be going the fastest that it will move. So why is this important? Well, because the formula for centripetal force is based on speed. It's mv squared over r. Now the r is not going to change. The m's not going to change either. But the v will change. And as that v changes, the centripetal force that's required changes too. So where does it require the most centripetal force then? Well, actually at the bottom when it's moving the fastest. And it requires the least centripetal force at the top. Now what makes this problem especially difficult is there's actually going to be a trade-off between the force of tension and the weight of the object. See, the weight is a force like any other force. It can contribute to the centripetal force in some circumstances. So where does it contribute? Well, I'll tell you where it doesn't contribute. It doesn't contribute at these positions here. The reason why is the weight is what we would call tangential to the circle. And for that reason, the weight does not help pull the object in towards center, and it doesn't push it out either. It wouldn't do anything when it comes to the centripetal force. In fact, what that would be called at that time is a tangential force. And we sometimes call that F tan. All right, so this tangential force will definitely slow the rock down as it heads toward the peak. That's what a tangential force does. It either speeds up the object or slows it down, but it can't change the direction. The force that has to change the direction will actually be this force here, which is the force of tension. And so at this time, the force of tension equals the centripetal force. Together, the centripetal force and the tangential force make up the net force on the object. So those are just really important points in the path of the particle. Because there we can clearly see the separation between the centripetal force and the tangential force. All right, so what happens at the peak then? At the peak, we want the string to go almost slack, to the point of being slack where it doesn't really have to exert a force, and we can let the weight of the object take over as the centripetal force. So interestingly, at the peak, the weight of the object becomes the force that keeps it moving in a circle. and the string can do nothing at that time. So as we're headed there, you can imagine that the force of tension goes down from what it was. And here it would be low as well. But when we do get to the peak, the Ft becomes 0. So toward the bottom, what happens? Well, here we have to maintain a large upward centripetal force, which means that the tension has to be really huge there. That's because it has to counteract the weight. So where would the string break if it was going to break anywhere? Definitely when the rock is toward the bottom. All right, now using this information, we can find out what speed the rock has to be moving at the peak in order to maintain its circular motion. We'll use the centripetal force formula, but we'll let the centripetal force be the weight of the object at the peak. So we would have that, and we just have to plug in, and then we can solve for V. So the mass was 1.7 kilograms. G is 9.8. And then our radius was 0.45 meters. We need 2.1 meters per second at the peak.